scattering problem is inherently non-unique because we can never do any super resolution thing. So it means that if I have a scatter rod, and if I add some high frequency features inside or on the surface of this scatter rod, this is not distinguishable by my experimental data. These high frequency features will only add to evanescent waves. And those evanescent waves are localized, and they never reach the receiver. So how do we overcome this problem? We overcome this problem by adding this term. Adding this term makes this matrix system positive definite. If this has 0 eigenvalues, then it will be padded with non-zero eigenvalues coming from this term. This term is always invertible. You can always prove that this is a positive definite matrix, and hence invertible. So, but you're distorting the problem by adding this term. The original problem to solve is actually just this term over here. You're adding a small term. So this is called the tuning parameter. It should be as small as possible. I think that sometimes it's also given credit to the Russian, Tikhonov. Tikhonov regularized. So I think maybe he figured it out first, I don't know. But anything that has to do with numerical linear algebra always goes to the Russian. Krylov, what have you? Krylov, maybe so the left. Left is not so much of a loss. Lyapunov, maybe now Tikhonov. What else? Lots of knobs around. So Tikhonov regularized, he got his name attached to this. So when you do this regularization method, you add this thing, but make this as small as possible. And then you get this equation, but what does it mean physically? What it means physically is that I'm adding a term that actually is the norm of the object function that I'm trying to reconstruct. That term actually comes from a term like this. So this is like minimizing the energy of the unknown in addition to the experimental data. This is to ensure that the experimental data's error is minimized. But in addition to minimizing the experimental data, I also minimize the norm. Okay, I also minimize the norm. And if I minimize the norm, then I can ask you a very simple question. If the norm is measured with an L2 norm, or squared norm, so if I ask you a very simple question, if I have this function, and then I have this function which looks something like this, but on top of it, I add some high frequency data. Just by eyeballing these two figures, which one has a smaller norm? If I use that to measure the norm, which of these two functions will have a smaller norm? The smooth one will have a smaller norm, right? The smooth one will have a smaller norm. You can kind of do this in your head. That you Fourier transform this. You Fourier transform this. This might be band limited, something like this. And then you Fourier transform this. It will be the same function, but maybe with some features at the far end. And if you take the norm of this function, according to the Pascal-Best theorem, it's the same as taking the norm in the Fourier space. When you take the norm of this and the norm of this, they are equivalent to each other by Pascal-Best theorem. This definitely has a higher norm. So if you try to minimize the norm in addition to minimizing the experimental error, you actually are squeezing out the high frequency information. Okay, you squeeze out those high frequency information, and then the solution becomes unique. Okay, there's one way to look at it. Of course, the other ways of solving this problem is Aditya has suggested. You can do SVD of this thing. Keep only the non-zero eigenvalues. And then invert. But that is very expensive. In terms of computational complexity, what is SVD? N cubed, right? This one I can use iterative methods to solve this problem. I can solve this equation iteratively. And I can do it in n squared time or n log n time, depending on the fast algorithm I have for matrix vector products. Okay, I can reduce this to the solution time for that. Okay, so never do SVD because it's too expensive. It's n cubed. Okay, so when I do this, then I'm essentially squeezing out the high frequency component, and the solution is unique in the sense of minimum norm. So this is also called a minimum norm solution. Actually, we actually find minimum norm solutions all the time. You don't realize that. You don't realize that. There are a lot of things in this world that are not unique, but we don't realize that. Like when we do Fourier transform and Fourier inverse transform. Okay. And when we do Fourier transform and Fourier inverse transform, it's actually non-unique. Because when I do Fourier inverse transform, I can add high frequency components to my data, and I wouldn't realize it. A simple low pass filter. Okay, if I have a low pass filter, if I pass a signal through it, and if I have something that comes up, and then try to construct the input from the output, this is not unique. But we never realize that. We just zero out the high frequency component and do a Fourier transform, right? Without realizing it actually that we're actually seeking the minimum norm solution. So if I give you the output, tell me the input, most students will just zero out the high frequency component and give an estimate of the output, of the input, without realizing the fact that we are actually seeking the minimum norm solution by so doing. So Fourier series and Fourier series inverse are always minimum norm. If you look at all the things that you have in the Fourier series, and Fourier inversion is also minimum norm. Okay. And so if you seek this solution, and then you seek a correction to the solution after that, you can say you guess the object function is given by this. Okay. After I find the correction to this thing by that procedure, I have a new update for my profile, and I can use that as a background. Okay, I can use this to feed to the background for the next iteration, and then seek my KR. Okay, now this is KR 0, KB0, KB1, and then I can iterate. Keep changing the background as I get an update. I call this the distorted one iterative method. And then you can converge to a rather good solution. But the key thing is still the fact that you have to solve a lot of these things numerically, and it's still very expensive. It's very, very expensive because you have to solve a forward sketching problem. This essentially is a forward sketching problem if you look at it. You're computing the scattered field due to an incident field of some sort. So it's still quite expensive. Another thing that you should realize is that if you do diffraction tomography, when you do diffraction tomography, you have Fourier data on the circle, and then you invert the data by Fourier inversing on this data. You zero pack outside with 0. You actually also are seeking a minimum norm solution in that sense. Even the diffraction tomography problem is not unique, because you only collect data within this circle. I can dump data out there, and they will produce the same scattered field, and you wouldn't know that you actually have a different object. But we always assume that it's zero outside, and that actually is a minimum norm solution as well. So you iterate on this, you get the distorted Born iterative method, and then you can keep going and going. Of course, you can also do this problem by singular value decomposition, but I think that's not popular. It's too expensive. Okay. So are there any questions? If not, then I'd like to have you fill out the course evaluation form. Since I have gone over, since I've already written the solution for the take-home exam, I can also go over the solution with you after you fill out the form. Okay? So I don't think we need to have the next lecture, unless you want to. You want to listen to the last lecture of the professor. Okay, most graduate students say no, right? I have to sign the form.
What will be the next lecture for? Like, what's the topic?
Oh, I haven't decided.
Maybe
you can request some topic, then I can see.
Maybe you can keep it as optional if people would
if they would
like to attend.
Okay.